Last time we started to dorsal. Frequency response model. So we have our plate, we have chord, your hinge right here. So this distance is AB, this is B, this is negative B, half chord. The plate is moving horizontally with a velocity U. This angle is the angle of attack, and this point is the hinge line. This point is your hinge. Alpha dot is here. And we also have H dot vertical, right? You have a question? Please stop me. So we have our airfoil or flat plate is doing this kind of kinematics, pitching, plunging while moving with a constant speed. And we want to determine the lift. We said the way to dorsal set up the problem is that he divided the problem into non-circulatory and circulatory, right? For the non-circulatory part, we don't have any circulation, we don't have vortices, so the type of singularity he used over the cylinder was source distribution. And we solved this last time. If you remember, the tangential velocity at any theta due to this source distribution, which we related to the motion, was 2 times u sine alpha, or u times alpha, h dot minus alpha dot AB. This is cosine theta plus alpha dot B over 2 cosine 2 theta. And if you can identify what's this bracket, this is the normal speed at what point? So u alpha is the normal speed due to u and the angle of attack at any point. The same for h dot. Alpha dot AB, so alpha dot is multiplied by AB as an R. So this is the normal speed at what point? Normal speed at what point? The center point. So this is V of half. In particular, it's negative V of half. V is the normal speed, okay? So this is V theta at any point. From the V theta, we got phi, and from phi, we got the lift. Non-circulatory was negative added mass times the acceleration of half chord point. So it's d by dt for this red bracket, okay? Where the added mass is the mass of the surrounding cylinder of fluid, estimated according to this theory to be pi rho b squared. Okay? So what we found is not really a lift, but more of a resistance, right? If you want to accelerate your airfoil, you need to accelerate the surrounding fluid, or it's as if the surrounding fluid is resisting you. So you need to overcome this force as well. So at the end of the day, if I'm going to pay some force to accelerate this solid, it's not only its mass times the acceleration, but there is an added mass that I'm going to pay its acceleration as well, added mass of the surrounding fluid. Okay? So it's more of a resistance than a lift in the sense that we know. Because like we know, actually the lift, our usual notion of lift, the generated lift, is due to mainly due to circulation within a circulatory flow. So here, lift is generated. So we need to see how to account for that. We need to see how to generate our lift, which is mainly due to circulation. So our setup will be, we will put some vortex in the way because we're unsteady, right? And we'll see the effect of this vortex on the plate. Okay? One thing to note before moving, maybe I'll write it here. So remember we have, this is our formulation, right? We will write this part over and over again. So this is our formulation. We have the PDE, the governing equation, it's Nabla squared phi or Nabla squared f, the complex potential is 0. Okay? And we solve this subject to the no penetration boundary condition. What else? What else do we need to? I'm sorry? The Coulter condition. What else? The conservation of circulation. So these four are sufficient to solve any problem within potential flow. Okay? So here, for the non-circulatory part, how we solve the PDE? Well, we use singularities that naturally satisfy the PDE. So this is already taken care of. What about the no penetration boundary condition? Did we satisfy the no penetration boundary condition here? Yes, we did. This is asking for the cylinder to be a streamline, asking for the radial, the normal velocity of the cylinder to be the normal velocity of the motion, right? So we did this, we did the no penetration boundary condition. This is what allowed us to get the Q of theta, the distribution of singularities. Whenever we put singularity, it's unknown, and the no penetration boundary condition is a very good candidate to get that. So we got left out of that. We did not satisfy Cotta, because Cotta is responsible for the generation of circulation. We did not have any circulation, and you can check that immediately here. Let's get V theta at the trailing edge. So at the trailing edge, you have theta equals 0. This is the point corresponding to the trailing edge of the plate. Let's substitute theta equals 0 here, please. Cosine 0 is 1, cosine 0 is 1. So we have 2 times V half plus alpha dot B over 2. So if you are at half cold, okay, and you added alpha dot times half B. Half B, so it's quarter. So from half cold plus a quarter, now this is 3/4. So actually, this can be written as, this is negative 2 V 3/4. Again, it's negative the V 3/4 because the V is divided upward. So the V theta, the tangential speed in the cylinder domain, at the point corresponding to the trailing edge is something. It's not 0. And why you want it to be 0? Because I'm reminding you, U is equal to V theta at any point divided by 2 sine theta, right? In particular, at the trailing edge, you put theta equals 0 here, theta equals 0 there. So the denominator becomes what? The denominator becomes what?
0.
Becomes 0, which means U goes to what?
Infinity.
Goes to infinity. The Cotta condition is not satisfied. Okay? So the non-circulatory part alone does not satisfy the Cotta condition. We did not need to. Okay? Now we're going to add circulation. So I will impose singularities in the flow now of circulatory nature. So we'll add vortices. Okay? We will add vortices, yes?
I don't see why U times alpha is part of V at the half chord.
It's coming from U sine alpha, but sine is like alpha. U sine alpha, this is U. U cosine is tangential, U sine is normal. And this is the normal speed at any point due to U. The same for H dot cosine alpha is the normal speed at any point due to H dot. So these two terms are the normal speed at any point due to the angle of attack motion and the plunging motion. But this guy is different from a point to another due to the pitching motion. It's alpha dot times the point, the distance from the hinge. So here is the hinge. If you multiply by AB, you get the velocity at the half chord. So this makes the whole thing is the total normal speed at the half chord point.
It's normal speed. That's why we're not using U
V.
cosine alpha. Okay.
Yes, but we're working in a small angle approximation. I mean, this is all to dorsal. But you can go through the derivation again and relax this assumption. It will not hurt anything. You can keep sine alpha, cosine alpha, whatever, it doesn't matter. Okay, so we're done with the non-circulatory part. It just gave us some physics here that we need to accelerate some part of the fluid surrounding to the airfoil. Okay, but it doesn't give us anything about the lift generation, how the lift generates. Okay, we need to induce singularities in the flow, circulatory singularities. So this is very important. This is very important to stress. So if you go and solve your PDE, Laplace core phi equals 0, subject to the no penetration boundary condition using any CFD method without intentionally putting wake singularities, without intentionally imposing the Kutta condition, this is the most that you can get, the non-circulatory loads. You will not get our usual lift mechanisms, okay? This is very important to stress. Yes, Lee?
Is non-circulatory lift like real lift?
Yeah, it's a force.
But you said
But
that.
it's a force in the sense that, okay, it's proportional to acceleration.
Oh.
So if you accelerating up and down, for example, well, you cannot keep accelerating. Okay, it's opposing to the acceleration. Okay, so if you're accelerating down, it will give you upward lift. Very good. But I cannot keep accelerating down all the way because I'm spending distance. So at some point I'll have to come up again, and if you do that, you will get net zero lift because it's you'll get positive lift and then negative lift, right? When you're accelerating down, you get positive lift upward. Then when you're coming up, you'll get negative lift downward. The net over the cycle will be zero.
Okay.
It's a force. It's a lift force. It's proportional to the instantaneous normal acceleration, but it's not our usual lift mechanism. It's something new that we only see in unsteady flow. This is coming out of the unsteady Bernoulli equation, in particular the d phi dt term, the partial phi partial t term. Okay. Yes.
So you mean that overall there is no non-circulation lift? I mean,
Net.
yeah.
Well, in instantaneous, this relation is in instantaneous, in the sense that this is at any particular t, this is at any particular t.
Okay.
Okay?
I think.
So this time, yes, I'm getting lift. Overall, on a net cycle, where this A has a zero mean, this guy will have a zero mean also.
Okay.
Now this is our real stuff here. This is again very important, okay? If you go and solve your PDE, because this is very confusing, I'm sure. You go and solve because, come on, this is potential flow, right? It's governed by the Laplace equation, and this is the only boundary condition that we need to satisfy. After you solve this, you get the velocity field, go to the unsteady Bernoulli to get the pressure. Well, that's okay, but if you don't intentionally add circulation into the flow, you don't intentionally account for the Kutta, this is the most that you can get. Okay, okay, so what Tudorson did is that, well, okay, he added circulation, a vortex point, vortex in the wake. So now let's keep track. We will need to also satisfy all things here, okay? So first of all, I still need, I'll use red for the circulatory part. So I'll still need to satisfy the differential equation. Well, if you add a singularity gamma over 2 pi r, it naturally satisfies the differential equation. Any of the singularities that we know, uniform flow, source, sink, right? Any of the elementary flows, uniform flow, source, sink, doublet, any of these guys, they naturally satisfy the differential equation. Okay? So it's like here, we did not solve the PDE, we just added singularities that naturally satisfy the differential equation. That's fine. But this is of unknown strength, okay? I don't know it. Over there, it was also of unknown strength, and we used the no penetration boundary condition to get its strength. Let's see how we get this guy. So we naturally satisfy the differential equation, that's fine. Let's see how we will keep satisfying this. Why? Because if this is at a distance large x here, at some point on the cylinder, the velocity is perpendicular to this line. So it has a radial component and tangential component, okay? Has a radial and tangential component to the cylinder. So you might, if you put a vortex here of arbitrary strength at an arbitrary distance, you will induce a normal velocity to the cylinder. We adjusted over there the no penetration boundary condition such that the normal velocity is the normal velocity of the motion. We must maintain this, okay? We must maintain this satisfaction. So we'll see how to do it. And also, the law of zero total circulation, we need to maintain this. At the beginning, we didn't have any circulation. Now you're adding a vortex. The easiest way to do it, well, it's very easy. If you're adding a vortex here, I'll add a negative vortex of equal strength. This is very easy. So I satisfied this guy very easy. Okay? And you just solve it homework 2. You're supposed to submit it right now. You should tell me how to satisfy the no penetration boundary condition. If I have a vortex at a location x, and I'm looking for this distance d of the other vortex such that the cylinder remains a streamline, i.e. such that there is no normal speed, the radial speed is 0, radial velocity is 0. What's the distance? What was the solution? What was the solution? If the radius here is a or something, what's the solution?
A squared over
A squared over this distance. Very good. So our distance here is b over 2. So I already know that to maintain the cylinder as a streamline, this is your homework problem 1, i.e. the v radial is 0. D has to be b squared over 4x. That's very good. Okay? So this is satisfied by selecting an appropriate D. So this is how Theodorsson formulated the problem. But just adding a circulation here at x and another circulation of the same strength at this particular distance, we do two things simultaneously. We did not disturb the no penetration boundary condition, which is already satisfied from before, and we satisfied this gamma. Okay? We still didn't touch contact, and you can see now that this gamma, we added gamma, but it's unknown, right? We added gamma, but it's unknown. And the no penetration boundary condition doesn't give you anything more. It already gave you this distance. Okay? We need an equation to determine gamma. We are in a circulatory framework, and we need an equation to determine circulation. Well, unfortunately, we have nothing but the Cotta condition. Okay? The Cotta condition is always, the back of your head, is the one that gives you the amount of circulation shed behind the airfoil or the cylinder. So how to get it? We got V theta non-circulatory at theta equals 0. This guy was not 0, right? This guy was not 0. It was some number related to the angle of attack at the 3/4 port. Okay? Was not 0. And the fact that it was not 0 led to the U at the trailing gauge be infinite. Okay? So I'm going to add the second component of the tangential. This is the circulatory that come from these two guys. Okay? At the same point, the total should be equal to what? Total should be equal to what?
0.
0. And this is what condition?